Thank you, Mr. Chairman. Today I'm going to give a talk about the chemical application of nanoparticles. To start to present the results of my work, I have to make some background of early investigation, just for you to understand the origin of this research. So, in our department, we are interested in interaction of biomolecules with the surface of nanoparticles, specifically with hydroxyapatite, because hydroxyapatite is the main component of the bone tissue, and titanium oxide, which is, as Professor Jean-Marie Martra have mentioned today, is used to cover the titanium implants in order to make the interaction of implant with the tissue more interaction better. So as far as it was discovered, on the glycine molecules adsorbed on the surface of hydroxyapatite perform the spectrum typical for zwitterionic adsorbed species, while in the same conditions the glycine adsorbed on the surface of titania performs some appearance of new bands which are due to amide bonds. So if we have amide peptide bond formation of the TIL2, what can it give to us? What is the mechanism of this process? The amide bond formation is interesting from the both points of view, the fundamental and from applicative, as if now there is a great importance of rethinking of amide bond synthesis, as you see the recent publication in Nature, as if, for example, 65% of all drug molecules contain at least one amide bond. So, what do we know about the mechanism of traditional amide bond formation? Any organic chemist will tell you that in the raw mixture of carboxylic acid and free amine, the amide bond formation does not occur because carboxylic group needs activator. So traditionally organic chemists use a lot of complicated, expensive substances in order to activate the carboxylic group. But the modern task is to avoid the chemical activation in order to make the process cheaper and more effective. For this, this question can be solved by using the catalysts. Now there is still a few studies related to the using of catalysts in this process, and mainly they are based on the homogeneous catalysis, which is also not so effective because after the reaction we have to purify the target substance from the catalyst. And last few years there is a set of publications devoted to this process on the silica, zinc oxide and titania appeared, but from the best of my knowledge they provide no insights on the mechanism of this process. And the mechanism is very important here because if we know the mechanism, if we know the weak points of the mechanism, we are able to improve the process to make it cheaper and faster and so far and so on. So for this purpose we have chosen the commercially available type of titanium, P25, which was very well studied in the previous researches of our lab, and this nanopowder consists of particles of truncated bipyramidal shape with the most abundant surface 101 and truncated surface 001. As the model molecules for amide bond synthesis, we have chosen the simplest form acid, carboxylic acid, formic acid. As if we work with IR spectrum, we have to obtain the most clear spectrum as it possible to analyze it carefully and deeply. And the pentylamine was chosen because it is the simplest amine, which is available in pure liquid form without any solvents. So the first step of the reaction is the adsorption, stepwise adsorption of formic acid onto the surface of titanium. As you can see, the evolution, while adding the formic acid onto the surface of titanium, the bands typical for formic acid appears. Mainly it's antisymmetric and symmetric stretching bands of carboxylate and a CO stretching band of undissociated formic acid. After the careful, if we play with amount of formic acid, we can obtain the clear spectrum without the content of the undissociated bands. Besides, as far as we know from the literature, the shape of the spectrum, the position of main bands, can give us information about the adsorptive complexes of formic acid on the surface. Which complexes it may be. There is three main type of complexes. Is bidentate bridging is the one when when each oxygen atom is interacting with different titanium atom. The monodentate complex in which only one oxygen atom interacts directly with only one titanium atom. And bidentate halatin, it is the case when two oxygen atoms are interacting with one titanium atom. Using this approach, we have determined that the complex of formic acid onto the surface of titanium P25 consists mainly of bridging complex and some small amount of bidentate complex. So the second step of the reaction is the admission of pentylamine. During the stepwise admission, we can observe the consumption of the main bands of formic acid and appearance of new bands due to CO, stretching mode of CO of amide bond. Moreover, the appearance of the new product was confirmed by high-resolution mass spectroscopy. So the product with the product of condensation of pentylamine and formic acid appears into our system. So now we have returned to the initial mechanism of the amide bond formation, and here we can see that in some way titanium surface act the role of this activator, and it activates the carboxylate moiety towards the nucleophilic attack of the amine. As far as we can see here, the carboxylate moiety is the negatively charged moiety group, and also amine group is also electron-rich group. And how can two minus combine to make reaction? So the only explanation is that titanium surface withdraw the electron density from the carboxylate group towards the surface. So if there is any dependence on the structure of the withdrawing, of the effectiveness of this withdrawing on the structure of the surface of the catalyst. For this purpose, we have chosen two more materials to make the same reaction, make the same experiment. The one is TO2 merc, which is available, commercially available, and also it was studied in previous activities of my lab. It's around particles, significantly larger than in case of P25, and hydroxyapatite particles, which, as we have determined before, are not able to promote the reaction of amide bond formation. So what did we get? Let's get a look to the two types of titanium. Green is P25 and blue is merc. The situation, in principle, is more or less the same. We see the consumption of the amide bond of the carboxylate species, but in the case of merc, this consumption is significantly smaller than in the case of P25, and the main part of the band remains resistant towards the amidation. And when we get a look to the case of hydroxyapatite, we can see only consumption of the undissociated formic acid and its conversion into the dissociated state, which means only salification. How can we explain this? When we, using our method of determining the type of the complex, see which bands are consumed, we can tell that in the case of merc, only bidentate species were consumed, while unidentate species of merc and unidentate species of hydroxyapatite are not consumed and remains resistant towards the amidation. So the activation of adsorbed carboxylates towards amidation depends on their coordinative structure on the surface of catalyst. As a conclusion, I can tell that reaction of amide bond formation on the TO2 nanoparticles occur. TO2 surface plays the role of the activator of carboxylic moiety through the withdrawing the electron density and making the carbon atom more able to undergo the nucleophilic attack of amine. And the effectiveness of such an activation depends on the type of the complex of formiate adsorbed on the surface. And in further research, we are to concentrate our attempts in finding the material which is selected towards the formation of bridging complexes of formates onto the surface. Thank you for attention.
Thank you. Questions?
Thank you for the nice talk. Are you thinking to make or to apply some quantum mechanics calculation to get some more insights in this?
Maybe.
Energetic and so on.
Maybe it's only half a year of my PhD. Maybe later.
The role of the nature of the surface in respect to the fact that it allows two negative charge to interact anyway for the molecule.
Okay.
Something like that?
Understood. The surface is withdrawing the electron density
Yes.
from the carboxylate.
Yes, the fact that it depends on the surface nature, is it due to the fact that some facets may be more charged or less charged than the other ones?
Maybe, as we did not do such calculations or such. The purpose was applicative, just to explain the mechanism in order to improve the process. Maybe happens something.
Didn't you try any other inorganic materials which could form some similar bonding with carboxylate group and then promote the formation of amide bonds via the same mechanism?
Not yet. We have tried only 3 materials, hydroxyapatite and 2 types of titanium, but everything is...
Only titania works?
We tried only titania, and as far as I told in previous publication, there is people use the silica, zinc oxide, or titanium nanoparticles.
Okay. So we might close that talk and go to the next one. So thanks again.